In 1931, engineers faced a problem that had never been solved at this scale: how to pour 3.25 million cubic yards of concrete without waiting over a century for it to cure. The Hoover Dam required more concrete than any structure ever built to that point, but concrete generates heat as it hardens, a chemical reaction between cement and water that releases thermal energy for years. In a normal building, this heat dissipates naturally through exposed surfaces. In a mass concrete structure like Hoover Dam, with walls up to 660 feet thick at the base, heat would be trapped inside. Calculations showed that if the dam were poured as a single monolithic block, the concrete would take 125 years to cool to ambient temperature. During that time, the surface would cool and contract, while the interior remained hot and expanded. The resulting thermal stress would crack the dam into fragments. The solution required 3 interlocking systems: physical division of the concrete mass, active heat removal during curing, and permanent structural integration after cooling. Fact 1. Why heat generation made conventional pouring impossible. Concrete curing is an exothermic reaction. When cement powder contacts water, complex calcium silicate compounds form crystalline bonds, releasing heat. In a thin slab, this heat escapes through exposed surfaces within days. In a structure the size of Hoover Dam, heat had nowhere to go. The dam's base is 660 feet thick. Heat generated at the center would have to travel over 300 feet to reach an exterior surface. Internal temperatures would rise above 160 degrees Fahrenheit and remain elevated for decades. As the surface concrete cooled first, it would contract. The hot interior would still be expanding. This differential movement creates tensile stress, the exact force concrete cannot withstand. Cracks would propagate inward, fragmenting the structure. Fact 2. Block division strategy, segmenting the monolith. The first solution was spatial. Divide the dam into independent blocks that could cool separately, then bind them together after curing. The dam was segmented into approximately 230 vertical columns, varying in size but typically rectangular in cross-section. These columns were separated by temporary vertical gaps called contraction joints. Each column was further divided into horizontal lifts, layers 5 feet tall, poured sequentially from bottom to top. This configuration created manageable thermal units. A 5-foot-tall block could dissipate heat through multiple exposed surfaces. Pouring did not proceed uniformly. Crews worked on multiple non-adjacent columns simultaneously, ensuring that no 2 adjoining blocks generated peak heat at the same time. Once all lifts in adjacent columns had cooled to specification, the gaps were filled with concrete, locking the columns together. Fact 3. Embedded pipe network. The core of active cooling segmentation alone was insufficient. Even divided blocks would take many months to cool naturally. Engineers needed to extract heat mechanically from inside the concrete. The solution was an embedded refrigeration network. 1-inch steel pipes were placed inside each block before concrete was poured. These pipes formed a grid with tubes running horizontally in parallel rows. In total, 582 miles of steel pipe were embedded in the dam. The pipe system was not structural. It carried no load. Its sole function was thermal transfer. Cold water entering the pipes absorbed heat from the surrounding concrete, then carried that heat out of the dam entirely. Fact 4. Refrigeration plant capacity. A dedicated ammonia refrigeration plant was constructed on site. The plant used ammonia as the refrigerant, a compound with high heat absorption capacity. Compressors, condensers, and evaporators operated continuously, chilling water to approximately 33 degrees Fahrenheit. Cold water was pumped from the plant to distribution headers across the dam site, then routed to individual blocks under active cooling. Flow rates were regulated by valve stations based on measured concrete temperatures. Water circulated through the embedded pipes, absorbing heat. Warmed water returned to the plant, where refrigeration equipment extracted the absorbed heat and re-chilled the water. This closed-loop system ran continuously during active cooling phases. Fact 5. Temperature monitoring systems. Temperature monitoring required real-time data from inside the concrete. Thermocouples, sensors that generate voltage proportional to temperature, were embedded in each block at multiple depths, creating a 3-dimensional thermal map. Engineers monitored for thermal stability, the point where the entire mass had reached uniform, acceptable temperature with minimal differential expansion. Cooling was considered complete only when thermocouples showed stable readings at acceptable levels. Data from thermocouples also informed poor scheduling. New lifts could only be placed on blocks that had reached thermal stability. Fact 6. Grouting the pipes, converting void space into structure. Once a block reached target temperature, refrigerated water circulation stopped, but the embedded pipes remained. 582 miles of hollow steel creating potential weak points. Empty pipes would leave void spaces in the concrete. Over time, water could seep into these voids, freeze during winter, and expand, cracking the surrounding concrete. Engineers eliminated this risk by grouting the pipes. Grout is a thin cement mixture, fluid enough to be pumped through small diameter pipes, but dense enough to solidify into a material approaching the strength of surrounding concrete. Grout was injected under pressure into each pipe network, displacing any residual water and air. As the grout hardened, it formed a solid core within each pipe. The cooling system transformed from temporary equipment into an integrated structural component. Fact 7. Contraction joint design, allowing movement, then locking it. The vertical gaps between columns were engineered joints designed to accommodate thermal movement during cooling, then transfer load after grouting. Each contraction joint was several inches wide. The faces of adjacent columns had vertical keys and keyways cast into them, creating interlocking protrusions and recesses. During cooling, these keys did not touch. The gap allowed each column to contract independently as it cooled. Concrete shrinks as temperature drops. Once adjacent columns reached thermal stability, the contraction joints were grouted. High-strength grout was pumped into the gap under pressure, embedding the keys into the keyways. As the grout hardened, it locked the columns together mechanically. The dam became a single monolithic structure only after every column had cooled and every joint had been grouted. Fact 8. Poor sequencing and thermal management construction did not proceed linearly. Poor sequencing was dictated by thermal logic. Crews worked on multiple columns simultaneously, but the sequencing was carefully planned. When a block in one column was being poured, neighboring columns would be at different stages. This staggered approach prevented thermal clustering. By offsetting pours in time, blocks benefited from cooler neighbors. Lifts were poured from the foundation upward in 5-foot increments. A new lift could not be placed until the one below had cooled to acceptable levels. The foundation blocks cooled more efficiently because bedrock acted as a thermal sink. Fact 9. Structural load transfer during construction. Each column stood independently during the cooling phase. Vertical load, the weight of concrete above, was carried by the column itself down to bedrock. There was no lateral load transfer between columns because the contraction joints remained open. The dam was not yet functioning as an arch. Arch dams transfer water pressure horizontally into the canyon walls through curvature. But until the contraction joints were grouted, the columns stood as separate elements. Water was not impounded behind the dam until the cooling process was complete and all contraction joints were grouted. Only then could the dam function as designed, as an arch transferring loads into the canyon walls. Fact 10. Why cooling was not optional. The cooling system was not an optimization. It was the only method that allowed the dam to exist as designed. Without active cooling, the dam would have experienced severe thermal cracking during construction. Even if natural cooling had been technically tolerable, the timeline was unacceptable. The project was authorized in 1928 with operational deadlines in the mid-1930s. The Hoover Dam has operated continuously since its completion in 1936. The structure remains monolithic, transferring enormous water pressure into the canyon walls, exactly as the cooling system made possible. The dam exists because engineers treated heat as a structural challenge. They built an invisible system, the refrigeration network, to make the visible structure possible. The cooling system was not supplementary, it was foundational. If you want to see more breakdowns of the hidden systems behind iconic achievements, subscribe to Grandeur Decoded.